Welcome back. Welcome back. So today we are on chapter 9. We want to study chemical bonding and Lewis theory. We want to see how Lewis theory can help us to understand how atoms bond. So why do atoms bond? They bond to form compounds with lower potential energy. That's the reason why they bond. To form compounds with lower potential energy. So according to Coulomb's law, the potential energy is proportional to the charge, but inversely proportional to the distance between the charges. So for charges with the same sign, the potential energy is positive. But for charges with opposite sign, the potential energy is negative. And let's take note, the more negative the potential energy, the more stable the compound. So let's look at types of bonds. When metals bond with non-metals, the type of bond they form is ionic bond. And in the formation of ionic bond, there is complete transfer of electrons. But non-metals can bond with non-metals, and the type of bond they form is covalent bond. In this bond, electrons are shared between the atoms. Then we have metallic to metallic bonding. This we call it metallic bonding. The nucleus of the metals are inside a pool of electrons. So these are the three types of bonding that we'll study. So ionic bond. Metals lose electrons to form cations, and the non-metals gain the electrons to form an ion. Result is oppositely charged ions are then attracted to each other, resulting in what we call the ionic bond. So ionic bonding is mainly between a metal and a non-metal. Covalent bonds. Non-metals have relatively high ionization energies, so it is difficult to remove electrons from them. So what they do, they share electrons. So when non-metals bond together, it is better in terms of potential energy for the atoms to share their valence electrons. So they share valence electrons. They share the electrons to form this bond, which we call covalent bond. So shared electrons hold the atoms together by attracting nuclei to both atoms. So those are the two main types of bonds. Determining the number of valence electrons in an atom. How do we determine the number of valence electrons in an atom? The group number on the periodic table will tell you how many valence electrons a main group atom has. So group 1A elements have 1 electron. Group 2A elements have 2 valence electrons. Group 3A elements have 3 valence electrons. Group 4A elements have 4 valence electrons. Group 5A elements have 5 valence electrons. Group 6A elements have 6 valence electrons. Group 7A elements have 7 valence electrons. And group 8 elements have 8 valence electrons. So that is how you know the valence electrons for an element. All what you need to do is to look at the periodic table for main group element, not transition elements. And you look at their group number. Their group number will tell you the valence electrons which that element has. So your periodic table, you have group 1, group 2, group 3. Those are group 1A, group 2A, group 3A. So let's look at Lewis theory, how to write Lewis theory, and how it can help us to come up with the structure of compounds. It will help us to show how these elements born and how their compounds are formed. Lewis theory. Lewis theory emphasizes valence electrons to explain bonding. Using Lewis theory, we can draw models called Lewis structures that allow us to predict many properties of molecules. So how do we write the Lewis structure? Writing Lewis symbols of atoms. We want to look at atoms, then we'll go to molecules. Symbols of elements represent the nucleus and the inner electrons. So for example, when I want to write the Lewis structure of sodium, the symbol of sodium represents the nucleus and the inner electrons. Then the dot around the symbol represents the valence electrons. Since sodium is in group 1, I'll put a dot. Please, I can put this dot anywhere. The main thing is that I put one dot to represent the valence electron. If it's beryllium is in group 2. I'll put the 2 electrons. You see, they are paired. If it is nitrogen has 7 electrons, but it has 5 valence electrons. So 2 are paired, 3 are unpaired. If it's oxygen is in group 6. It has 6 valence electrons. 2 are paired, but 4 are paired, 2 are unpaired. So that's the valence electron. That is how we write the Lewis structure for atoms. You represent only the valence electron. The symbol represents the nucleus and the inner electrons, or you call it the core. So let's write the Lewis structure for arsenic. So this is arsenic. Arsenic is in group 5. It has 5 valence electrons. So you see, simply write As, then to represent 3 which are not paired. So that is the Lewis structure for arsenic. Okay, you can see it here. So arsenic is in column 5A, therefore has 5 valence electrons. So you see its Lewis structure. 2 are paired, then 3 are unpaired. Lewis symbol for ions. Cations have Lewis symbols without valence electrons, because the valence electrons have been lost to form the cation. So for example, the Lewis structure for potassium is just K+. The Lewis structure for aluminum is just 3+. They have lost their valence electrons. But anions have Lewis symbol with 8 valence electrons. Because electrons are gained in the formation of anion. So let's take, for example, bromine. That's its Lewis structure. Let's look at oxygen. So this is lithium. This is the Lewis structure. This is the Lewis structure for lithium atom. This is the Lewis structure for lithium cation. This is the Lewis structure for fluorine. And this is the Lewis structure for fluoride ion because it has gained 1 electron. We want to talk about the Lewis bond theory. Atoms bond because it results in a more stable electronic configuration. They want their electronic configuration to be like that of noble gases. You remember we looked at the electronic configuration of noble gases in chapter 8, and we noticed that their subshells, the NS and NP subshells, are filled. So they have 8 electrons in their valence electrons. So they don't react. So atoms bond by transferring or sharing electrons. Usually this results in all atoms obtaining an outer shell with 8 electrons. We call this the octet rule. They want to have electronic configuration like the noble gas before them or the noble gas after them, closest to them. There are some exceptions anyway to this. Lithium and beryllium, they try to achieve the electronic configuration of helium, which is only 2 electrons. We call that the duplet rule. Octet rule. When atoms bond, they tend to gain or lose or share electrons to result in 8 valence electrons, Ns2 and Ap6. N is the principal energy level where the valence electron will start. Many exceptions like hydrogen, lithium, beryllium, boron attain an electron configuration like that of helium because helium has 2 valence electrons, a duplet. We also have some exceptions. Expanded octets. Some elements do expand their octet. They are elements in period 3 or below. That is period 3, period 4, period 5, period 6. Using empty valence d orbitals for bonding. So you have some exceptions like this. But generally, most elements want to have 8 electrons in their outermost shell. Lewis theory and bond ionic bonding. Lewis symbols can be used to represent transfer of electrons from a metal atom to a non-metal atom, resulting in ions that are attracted to each other and therefore bond. So let's say we want to see the bonding of lithium and fluorine. Lithium is going to transfer its 1 electron to fluorine and it's going to form a cation. The fluorine will accept that electron to form an anion. Then they will electrostatically interact to form what we call ionic bond. So let's see that. You see, that's lithium transferring its electron to fluorine. Let's see the result. So lithium now has a positive charge and fluorine has a negative charge. Then they are together. This is what we call ionic bond. So this is ionic bond. So that is how ionic bond is formed. You see this positive charge in lithium interacting with the negative charge in fluorine, keeping them together. So how do we predict the formula of ionic compounds? Using Lewis symbol. Electrons are transferred until the metal loses all its valence electrons. And the non-metal has an octet. Number of atoms are adjusted so the electron transfer comes out even. So let's take an example. Lithium has just one valence electron. Oxygen needs 2 valence electrons to have 8 electrons in its atom shell. So one lithium can transfer only 1 electron, but we need a second lithium to transfer the second electron so that oxygen can have an octet. Then you have the compound, even number of electrons. So that's the first lithium, the second lithium, and you see the result. Now we can predict the formula. So we have 2 lithium, the number 2 will go as a subscript, but we have only 1 oxygen atom. So this is how we can predict the formula of a compound using the instruction. Depending on the number of electrons which have been transferred and how many atoms transfer those electrons to make the other atom to become an octet, or how many atoms receive the electrons so that all of them can have an octet. Ionic bonding. The extra energy that is released comes from the formation of a structure in which every cation is surrounded by every anion, and every anion is surrounded by every cation. So electrostatic attraction is non-directional. No direct anion or cation pair. We don't have that in ionic compounds. Therefore, there is no ionic molecule. We don't have ionic molecule. We don't use the term molecule for ionic compound. Instead, we use the term chemical formula, which is an empirical formula. So simply giving the ratio of the ions based on the charge balance. That's all. So we don't use this term. We use formula units of chemical formulas. We don't use the term molecules for ionic compounds. So how are these ions arranged? The ions are arranged in a regular pattern called crystal lattice. So the crystal lattice maximizes the attraction between the cation and the anion, leading to the most stable arrangement. So you see, look at them, but see, look at the results. Very beautiful. Good arrangement. So we call that a crystal lattice. It has a regular pattern. You see, you can see a pattern. Just look at it. You see a pattern? There's a good pattern there. And if you notice, each is surrounded by four cations. And this cation is surrounded also by 4 anions. Just look at it where you see the pattern inside. It's so beautiful. So lattice energy. Lattice energy, the energy released when the solid crystal forms from separate ions in the gas state. And lattice energy is always exothermic. Lattice energy depends directly on the size of the charges, but is inversely proportional to the distance between the ions. So let's look at lattice energy, trends in lattice energy in ionic sizes. So this is a metal chloride. This is, you see, lithium is smaller than sodium. Sodium is smaller than potassium. Potassium is smaller than cesium. The cation, the anion is the same for all of them. But you see how it affects the lattice energy. The lattice energy becomes less negative as the size of the cation increases. So the lattice energy becomes less negative as the size of the cation increases. So let's look at an example. Order the following ionic compounds in order of increasing magnitude of lattice energy. Let's examine them. Calcium and strontium have the same anion. Bromine and chlorine have the same cation. So first examine the ion charges and order by sum of charges. So if you notice, calcium is 2 plus, potassium is plus 1, strontium is 2 plus. Then let's look at oxygen. Oxygen is 2 minus. Bromine is minus 1. Chlorine is minus 1. Strontium is, oxygen is 2 minus. So by looking at the charges, you can, this is strontium. You can arrange them, which ones will be larger. So you see, these ones have larger charge than this one. But you see the same anion, these ones are large, but the same anion. So this anion is bigger than this. So we're going to put this as the largest, has the largest magnitude of lattice energy before this. Then now we'll come to this one. This one now, they have the same cation, but you see, bromine is bigger than this. So this one will have more lattice energy than this one. So that's how we arrange it. So let's look at it. First, examine the ion charges and order by sum of the charges. So we are looking at them: potassium, chlorine, strontium, and oxygen. Potassium and chlorine, strontium and oxygen. Okay, yeah. So you see, these two are on one side and these two are on one side. So you see, that's it. These two are on one side, these two are on one side. Then now examine these ones now. So these ones are less than this. Now examine this. But you see, strontium is larger than this. So this one will be greater than this. Let's go. Then examine the ionic sizes of each group and order by radius: larger, smaller than small, less than smaller. Let's look at it. So this is larger than this. So this will have less energy than this one. So that is how we have this. Means calcium, if it's may put calcium before strontium. But bromine is less than potassium, it's less than calcium oxide and strontium oxide. But if you look, calcium and strontium, strontium is larger than calcium, so calcium should have higher lattice energy than strontium. Yeah, so wow, so that's it. So you see, yeah, that's the trend. You get the trend. So try and practice this. Practice the same thing on this. Try and apply it so that you have a full understanding of how it should be. Order the following ionic compounds in order of increasing magnitude. Let's look at the theory of covalent bonding. Theory of covalent bonding. Lewis theory says that another way atoms can achieve an octet of valence electrons is to share their valence electrons with other atoms. Share their valence electrons with other atoms. The shared electrons would then count towards each atom's octet. The sharing of valence electron is called covalent bonding. So covalent bonding and lone pair of electrons. Electrons that are shared by atoms are called bonding electrons. The electrons that are not shared by atoms but belong to a particular atom are called lone pair of electrons. Or we also call them non-bonding pair of electrons. So for example, we have this molecule. Let's examine and see the bonding electrons and the non-bonding electrons. So these are the bonding electrons, you see. Those are the bonding electrons. Then let's look at the lone pair of electrons, the non-bonding electrons. So these ones, let me change the color of the pen. So this one's like this. These are the non-bonding electrons. And you see they belong only to this oxygen. This two belongs only to this sulfur. This 6 belong to this other oxygen. So these are bonding electrons, the ones I circled in red, and the ones I circled in orange are lone pair of electrons, non-bonding electrons. Single covalent bond. When two atoms share one pair of electrons, it is called a single covalent bond. It has 2 electrons. One atom may use more than one single bond to fulfill its octets. 2 different atoms, hydrogen can form only one bond. It can have only one bond because it can have only a maximum of 2 electrons. So this is fluorine. You see, it has this electron which is unpaired and this which is unpaired based on the Lewis structure. Then they bring them together and they share it. So this is the shared electrons, two of them. So this is the bonding electron, and every other thing are non-bonding electron. So we represent a pair of electrons which is shared by a single line. So this is a single line. This represents a single covalent bond. This line represents a single covalent bond, and it has two electrons. So this is another example. Hydrogen has one electron. Oxygen needs two electrons. So you need another hydrogen. So the share is see, this is the electrons which have been shared. So single bond this way and single bond this way. So that is it. We want to talk about double covalent bonds. When two atoms share two pairs of electrons, the result is called a double covalent bond. 4 electrons are shared. So this is hydrogen. Hydrogen, each of them needs 2 electrons to complete their octet. So what happens? They bring their two electrons are there and they share. So you see, this is the electron they've shared. So this is the 4 electrons, and the result is that you have a double bond. That's a double bond. Triple covalent bond. When 2 atoms share 3 pairs of electrons, the result is called a triple covalent bond. 6 electrons are shared. So that's nitrogen. Each of them need 3 electrons. Look at their Lewis structure. So each of them bring the 3 electrons and they share. So everybody goes with 6 electrons. So see 6 electrons which have been shared. And the result is a triple bond. So we'll stop here and we'll continue with the class.